Chapter 30, Problem 10. Take a circular piece of wire and bend it in half as shown. Expose this wire to an external uniform magnetic field of magnitude 76 millitesla and then turn off this external uniform magnetic field. The horizontal semicircular loop and the vertical semicircular loop are both exposed to a flux. Turning off the magnetic field changes this flux. A changing flux creates a voltage, and the voltage causes current to flow. This question is asking, what is the magnitude of this created EMF or voltage, and what's the direction of the induced current that results? Step 1. As soon as I realize I have a conducting loop exposed to a changing magnetic field, I'm thinking Faraday's law. Step 2, there's Faraday's law, which I just automatically write down. Step 3 is where I really need to start studying the situation because there are a lot of different paths I could head in. My first instinct is to break this up into two segments. The horizontal semicircular loop is one segment and the vertical semicircular loop is another segment. Let's start with the horizontal segment. Step 5, I'm going to change the dot product integrand into a magnitude angle integrand. If I was given unit vectors, I'd stick with the dot product, and you can always figure out unit vectors even if they're not given to you, but the magnitude angle format seems to lend itself most readily to this situation. Step 6, I'm remembering what theta is referring to in my magnitude angle expression. It's referring to the angle between the two neighboring vectors, in this case the magnetic field vector B and the surface normal vector dA. Step 7, from this point forward I'm not going to drag along the negative sign. The negative sign is just the Lenz's law aspect of Faraday's law. It's just pointing out the fact that when you create a voltage, the voltage you create creates an induced current, and that induced current creates another magnetic field that opposes the primary magnetic field. Step 8, cosine of 45 degrees is a constant, so I'm going to bring that out of my integrand and actually to the left of the differential as well, which leaves me with the integral of b dA. This is where deep understanding comes into play. Step 10 is when I really take a close look. Do the magnetic field and surface normal vectors vary as a function of position, or are they linked spatially to each other? Step 11, the answer is no. I have a uniform magnetic field, which means it does not change as a function of position. The surface normal vector dA for the horizontal semicircular loop is pointing straight up, and it's pointing straight up everywhere on that loop surface. It's the integral that captures the spatial characteristics. It's the integral that you use to capture the flux at a given moment in time. The magnetic field is uniform, so that can come to the left of the integrand. The integral of dA is A, so this is what I'm left with at the bottom of this page. Here's the next major question you need to ask yourself. Do the magnetic field and surface normal vectors change as a function of time? Previously, we asked if they changed as a function of position. Now we're asking if they change as a function of time. Step 13, the answer is the magnetic field does in fact change as a function of time. It starts at a given value and is switched off during a given time interval. The surface area is not changing as a function of time. It's just sitting there stationary. So step 14 is our updated version of Faraday's law for this specific situation. Step 15, I'm a little bit worried because I don't have a function describing the magnetic field, so I'm wondering, how do I take a derivative if I don't have a function to differentiate? But I read the question statement again, and it says the magnetic field starts at 76 millitesla and reduces to 0 in 4.5 milliseconds. It's important to note that the magnetic field changes from 76 millitesla to 0 millitesla uniformly over that time interval. That's a key word. Uniformly reduces from 76 millitesla to 0 millitesla. This note here says to ignore the negative sign, just like I ignored the Lenz's law negative sign. Right now, I'm just concerned with magnitudes. I'll use right-hand rules to figure out directions later. I'm going to store this delta B over delta T result in my calculator's memory. Step 16, here's my answer. I looked at the position dependency of the magnetic field vector and the surface normal area vector, and I also looked at the time dependency of both vectors. I proceeded with caution, and this is what I get. I'm going to store this result in my my calculator's memory as well. Step 17. I know that a voltage is created in this top semicircular loop area. The question is, what's the direction of the current that gets created as a result of this created voltage? This is where Lenz's law comes in. Look at these magnetic field lines piercing this top horizontal semicircular loop, flowing from the top left to the bottom right. When the magnetic field is switched off, they continue to flow from the top left to the bottom right, but they begin to diminish. They diminish uniformly over a given period of time. So nature reacts by forcing the induced current that gets created to flow in a direction that will strengthen the magnetic field lines as they go from top left to the lower right. This secondary magnetic field is trying to oppose the change, and the change is a weakening of the magnetic field going from top left to bottom right. So the induced current will create a magnetic field that attempts to strengthen the magnetic field flowing from top left to lower right. It's as if nature is trying to do whatever it needs to do to maintain the original flux. If you use right hand rule number 2 and you grab this wire with your right hand and your fingers are curled in such a way to flow from top left to bottom right, your thumb has to be pointing in the direction shown, which is the direction of the induced current in the top semicircular loop. Here's a picture illustrating what I'm talking about. This is the horizontal semicircular loop. Grab it with my right hand. My fingers are curling in the direction that they need to curl because I need to restore the diminishing external magnetic field with the new induced magnetic field, and my thumb is therefore pointing in the direction indicated. If you're looking at this top semicircular loop from the perspective of the magnetic field lines, so you have to change your perspective a little bit here, that induced current I is flowing in a clockwise direction, again from the point of view of the external magnetic field that you're looking down. Step 20, we're done with this loop. Let's turn our attention to the vertical semicircular loop. Step 21, we're going to repeat everything we did for the horizontal semicircular loop. Notice though that I have a new surface normal vector. It's still making an angle of 45 degrees with respect to the magnetic field lines. So the EMF that we get for the vertical semicircular loop is exactly the same as it was for the horizontal semicircular loop. So I'm going to multiply that result by 2. Step 22 is showing the total induced voltage or total induced EMF that's created in a wire as a result of changing the magnetic field. Step 23, what's the direction of the induced current flow for this vertical semicircular loop? Once again, I'm noticing that the external uniform magnetic field is flowing through this vertical loop from top left to bottom right. As it's doing so, it's weakening over a time interval. I grab this vertical wire segment with my right hand. My fingers are curling in such a way to indicate a magnetic field flowing from the top left to the bottom right, which is something I want because I need to oppose the change. And again, the change I'm opposing is a weakening of the top left to bottom right flowing external magnetic field. So if I grab this wire the way I described, my thumb has to point in the direction shown. Here I'm doing the right hand rule on the vertical semicircular loop. I again grab the wire, my fingers are curling in the direction shown because I need to restore the diminishing magnetic field that's flowing from top right to bottom left, and my thumb is pointing in the direction of the induced current, which from the point of view of the magnetic field lines going through this vertical component is again clockwise, which is consistent with the clockwise flow existing in the horizontal semicircular loop.